and welcome back to this next session in our tutorial about agents JL and Julia. In the last session, we looked at how we can save the data from a parameter scan on our model. And the next thing we are going to do is have a closer look at our model and try to understand how we can integrate another aspect in our model. Currently, we have a so-called simple infection model where any person can infect their neighbor, and the infections have an illness duration, and we basically keep track of the state of the illness by having an integer variable that can have different values. We could have something like a recovered variable. We could move into a state 2 where people cannot be susceptible for a certain amount of time, and they can only become susceptible after a certain period of waning. And I think we can integrate this here by saying 2 would be recovered, and we would say immune, and we would then determine how long they have been in this recovered state when they turn immune. And the immunity in this case, we would put this in the parameter is immunity duration. Duration would be maybe 20 days, immunity duration. And this is obviously a parameter that we need to add into the model. So the immunity duration is mapped to the immunity duration. So basically we add the parameter to the initialization function, we add it to the properties, and then we need to change the behavior of the agent. In this case, if a person's health is equal to 1, then their illness duration is going down, is compared against the model illness duration. Then the person's health will be set to 2, which means immune. And we set their illness duration back to 0 because we want to now count towards the immunity duration. So if we have a person health is equal to 2, then we will first of all say person dot illness duration we will increase by the value of 1, and then we will test if person dot illness duration is greater or equal than model dot the immunity duration, then that person dot health becomes 0, they are healthy again, or susceptible, let's say susceptible again, and this person's illness duration is reset to 0 again. So we use the illness duration as a counter for both states, and in this case the states are completely deterministic. This obviously changes something about our plotting because the color only tests whether p is equal to 0, and now I think we should go back to a full function where we say we have, let's put this in here, where we have to check if p.health is equal to 0, then we want to return blue, else if a statement? Yes. Else if p health is equal to 1, then they are ill. Then we want to return red. Whoops, not redirect, just red. Else we want to return maybe green, and that would be, in this case, immune. And this should now allow us to run through a different state. But the problem is that the parameter scan and the where is the video thing? No, let's use the interactive version of this. The exploration basically counts the sum of the health variable, and that does not really make a lot of sense because we don't want to count the recovered people twice. We want to count the ones that have health equal to 1. And for that, we need a a different function that returns a value for the model, and this is a summary function. And for this, I will go to the agents.jl definition. So this is the website of agents.jl, and to show you if there's something that you don't know, how you can move on if you're trying to figure out how to do something. So there is multiple ways of doing this. You could obviously do the tutorial, but you can also look into the examples that are available. There's also a crash course on agent-based modeling. There is API, plotting, and interactivity. And this is where we want to go. We want to think about plotting. And we are here in this section, interactive ABM applications. And this is what we're seeing, and let's have a look what they're explaining. One could click the run button. Okay, one can further collect data while the model evolves and visualize them using convenience function ABM exploration, and this is what we're using. We have a function, and this is also, we can also use these functions as data. Let's see, what are they actually doing? So it has a function black A. If the breed is black, then this returns true, and we have white A. And we can count how often this function is mapped. So let's test that out if that works for us. So what we will do is, in the plotting region, we will have a function that is healthy P, which basically returns if p dot health is equal to 0. And so if I put this into an agent, and this one would be, let's call it not healthy, but susceptible and infected, then this would be 1, and we would have recovered, and then this would be p health is equal to 2. So if we have that, whoops, available here, then in the interactive exploration, we could in theory not just have health and the sum, but we could have the function, which is loaded here for susceptible, and we have the count, and we have infected, and we have the count. And let's test if that works as we expect it to work by running our model. Incomplete function. So it looks like, where did that happen? At the model.jl. Where is the syntax incomplete? So in model, the function is incomplete because, oh yeah, this if is never ended. And then obviously this doesn't work. So let's go back to interactive. The way I determined this was there are lines indicating wherever there an if should end, whenever an end is expected, and there was something missing here. So I saw that quite rapidly, and you should too. This loads all our functions. We initialize our agent set. We now have a tuple that has a function, and count, is count a function as well? Let's see in the description. It's not a function. It has statistic mean, but that we don't need. So let's see if that works. We use the ABM exploration tool after loading GLMakey, which always, if you're doing this the first time, it always takes a while. And now the library has been loaded, and now we have a look in our ABM exploration function, where this updated A data set is now being used to visualize the new type of model. And let's see how that works. And this should open up a window, which it does. And we have count susceptible and count infected. And we have 400 people that are susceptible and 1 that is infected. If we run a model step, one of them increases and the other one decreases. And let's run the model. Let's make it a little faster. And the green ones are now the ones that are immune. And interestingly enough, the immune ones, immediately when they become susceptible, they get infected. So this does not really change anything. It just increases the duration until people are, when their illness duration is reached. So obviously you would have to have another parameter in here. The illness duration is now between 5 and 15, but in the model, the initialize function now also has a, where is it? The immunity duration. Let's put the immunity duration in there as well. And we can have another function here, which basically says immunity duration, which is a symbol, should be something from 5 to 15 as well. So if we do this, we can run that again and now have a look at this reset model. Oh, it was still open and then it sometimes breaks. So let's see if I do that again and that again. Do we now get a new version of it? Can I reset the model? For some reason I can't reset the model, but I can I close this? Okay, I have to shut down this and I will have to, okay, it's frozen. So I'll kill this task and I'm back to starting the program all over again. And that's a problem with the ABM exploration. For some cases, if you change something fundamentally in the model, it can be that you cannot easily reload your ABM exploration tool. The tool is not designed to test between different models, but it's designed to test parameters inside of a model. So restarting is a very good option in many cases. So we're waiting for this to fully function, and now it should load the figure, and there it is. We can call this now, and now if we run the model, we can change the immunity duration, how long people will be immune, update. Not really sure where this problem comes from. Key illness duration not found. Let's increase the speed here. So to me, it looks like it's actually doing something. So if I increase the duration of the illness, it takes a while. It's actually, did it crash? No, it didn't. I'm not even sure if it's doing anything. Illness duration not found. Error and callback. Let's see if illness duration is, so the params are the parameters of the model. Oh, I think it is model illness duration. Maybe this is where we caused an error. That's a shame. So let's try that again. If I cancel this thing here and I just do reload all of it, you can press the play button up here to activate the whole file. And let's see if that was the problem, because we renamed the illness duration in our model to the model illness duration in the parameter, as well as in the dictionary for the properties of the model. So now if it's still, oh, the one downside to pressing the play button is you don't get to see which of the individual lines has finished executing. So in this case, we're just waiting for the whole thing to execute, and it is generating this interactive website in the background, and now it should be finished and we should have the tool here. So let's see what happens if I run the model. This seems to be, let's increase the speed, fine. And if I change the illness duration to be 15 and I update it, okay, it now works. It was a problem. And we can change the immunity duration. People are not ill a long time. And the immunity duration, does that have an effect on anything? It doesn't seem to have such a big of an effect, right? How long people are ill. because no one ever becomes susceptible again. Why does no one ever become susceptible again? Oh, because the likelihood of getting an infection is so high because we have so many people. So if the immunity duration increases, then people cannot get infected. Can we speed this up a little bit? And let's assume that people are ill for or are immune for a long period of time. And the susceptibility goes all the way down to 0.0. Then we actually have people get not ill for some reason. Okay, let's close this. Does this work now? Apparently closing it might even crash it, but maybe it's just finishing up, so we don't know. So an interesting question here would be, why does the immunity, when it's larger than, let's see, if health is equal to 1, then the illness duration is increased. And then if the illness duration is larger than the model illness duration, we set that to 2 and set the illness duration back to 0. And no, that should work fine. So this is, whoops, wrong line. This is a person is infected. And here we have the code for person is immune or recovered. And now we've moved from our SIS model to an SIRS model, which is one of the most famous infectious disease models that we have, because it applies to lots of different illnesses where you become not permanently but temporarily immune against the disease. And obviously some of these parameters are not realistic. For example, it could be that the immunity duration, because we have now considered this to be days, it could be that we have between 5 to 15 days, but the immunity could well last maybe from, let's say, 15 days, I mean, that's even a small number, to maybe 180 days. So people could be immune for a very long time. And if we execute this, you will see that if we open our Julia thing again, and now I will have to zoom in to make the controls more visible. If I run the model and increase the speed, I can now change the immunity duration to periods that are a lot longer, but it doesn't seem to work. Why is this not updating the immunity duration? It's just, oh, are we comparing against the right thing? Let's see. We are comparing if the illness duration is larger than the model immunity duration. We're checking the right thing. Are we setting the right thing? So here we have the immunity duration. The default is 20. And in our properties, we're setting it here. Yes, that should work. So I'm wondering why people are not longer immune than they should be. They should stay immune for 180 reset model. Though they just turn green and immediately they turn back red. Oh, that's an interesting thing, because if a person is immune, they can still become infected. The infection does not prevent infection, and the disease state of immunity does not prevent infection. So if the neighbor is health, so this can only occur, and we should put it therefore, if person is susceptible, then we want to do all these things. And for that, it makes sense that we do this. So only if the person is susceptible do we check whether he can get affected. Person is susceptible. So now the whole thing should make much more sense. And that is also a thing that you should do, and that's why interactive exploration is helpful. You will make mistakes, and mistakes do not immediately show up if you have very subtle changes, if you have to make you should test whether drastic changes affect your model in a way that you didn't expect. So we have this visualization, and if I now run the model, let's do it like this. So people are ill for 10 days, and let's reset the model, update. Now we don't ever see an infection. No one is ever getting infected except that first person when we reset the model. So obviously something is wrong in our model. So if the person is, if person is 0, no, if person health is 0. Person is never 0, and that's why we never had infection events. Let's go back here and try that again. Are we there yet? Apparently we are. So let's run the model. People will get infected. And after 10 days, that's when almost everyone is infected. In our case, we will see that the first people will get immune. And now we should really see the immunity kick in because people are staying immune for 20 days. And we see the model as the agent-based model's problem that no one is infected and we can no longer have infections happening. So this is a case where a model that we have where we reduced our system to a state of 400 agents, and as soon as the disease dies out inside of this population, the disease is gone. And this is in some outbreaks, this is the case. Some diseases never reappear on the surface of Earth, but for cases like COVID, it can be that a subgroup of population becomes immune, but since there are so many more agents, there can always be a remaining pocket of people that can become infected. And we can easily test this by doing the following. Instead of changing these parameters, we go in here in the initialize function where we initialize our model, and we have a look at the initialize function, and then there's two parameters, the grid dimensions and the total agents. And we can put this in here as well. So we change the grid dimensions and the amount of total agents to values that are bigger than this. And let's do 100 times 100, and this would be 10,000 agents. By the way, there's a way of writing numbers in Julia that makes it easier to read. You can put in underscores to highlight the decimal separators without actually putting in a decimal separator, which is a command in many cases. So if you would add a comma here, that would separate, for example, values in a tuple or something similar. Let's see if this works. Yeah, what we now see, and this is what makes it a little bit harder to understand, is we have now 100 times 100 agents, and we need to zoom out sufficiently far that we see what's going on. And let's run this model, and we can increase the speed. This is how the disease spreads. And in this case, we also see that the disease dies out. So let's reset the model. And the reason for that is that there is no way that in this lattice-shaped relationships, there is no way that the illness can let's reset the model, can actually go back into this area, because it spreads in this direction. So is there a way of how we can fix this without changing drastic assumptions about the model? We could, in theory, assume that there's random connections and people move more randomly, but this will enforce that we have to put in a lot more work in our general model setup. So one thing that we could model is that we will have, first of all, we could have something such as an influx of infections, and in the most simple form we will do it maybe here, immunity duration, and then we would have like an influx probability, and the influx probability is, we have to pick it sufficiently small, and we put the influx probability here as a model parameter. We create a symbol, we assign the parameter of the function, And we can here, in the agent step function, we could say, and this is maybe, the agent step function is now called on every agent, and this means in every iteration is called 10,000 times. So this parameter depends strongly on the amount of agents that we have if we run it in the agent step function. And this is what we're going to do. If random of model.rng, this is a value between 0 and 1, is less or equal than our model.influx probability, which should be rare if it's a small number, then we do something. We do P is a random agent from our model, and P, and then we do the P infection if that person is not recovered. So then we do if P.health is 0, then P.health becomes 1 end. And this is influx from outside of the model. This is the most simple way of how you can model influx from the outside, and let's see what will happen if we do this. Zoom in, make it fast, run the model. And we see that we have spots where there's new infections coming in, and actually that's happening quite frequently. And this looks mesmerizing, and we see that we have waves of immunity, waning immunity, and increasing infections. And some of them are high waves, then we have lower waves. And if we increase the speed a little bit, let's see if we might see some more patterns. But I don't think that we're going to see more patterns, except for we have some high waves, then we have lower waves, high waves, and lower waves. And I would not see a pattern beyond that. So let's stop this model. Maybe models don't run the model. We could change this parameter to let it not happen as frequently. So the default of this variable should probably be in this case. Let's do it like this, and let's do the grid dimensions 100. Whoops. 100 times 100, and we have 10,000 agents as a default as well. And I add another 0 here, and let's see how rarely this occurs. It should occur sometime, but not all of the time, and then we should see much more rare occurrences of these influx infections where fast run. And there's one other infection, and there was another one. So this looks very interesting, and maybe this is one order of magnitude too little. Let's keep it like this. We could also put this into a parameter which we can change in the exploration, but this is not what we want to do now here. The next thing that I think is important, but it's part of the next video, is trying to understand the impact of information and the informedness that people have, and the overall informedness, how that is going to change the behavior of individual agents, because obviously we don't want to only model an SIRS model, but we also want to understand how information can affect an individual's behavior. And for that, we'll have to wait for the next video. I hope you enjoyed this video, and I'll see you in the next one.